So that's kind of what's happening. Let's jump back into where we left off last time. And that was inverse trig functions. So remember, inverse trig functions are doing the opposite. Trig function, I'd be putting in an angle and getting back a value. Now I'm going to be putting in a value and get back an angle. And we said that with this, the big thing is that when we're doing inverse sine, inverse cosine, we have to limit our output. For cosine, in order for our inverse function to be 1-to-1, we're going to have to limit the domain to negative 1-to-1. That's always the domain of cosine anyways, or excuse me, the range of cosine. So, but in the domain of cosine, the range of inverse cosine, we're going to limit that from 0 to pi. And that's only going to give us the top half of the circle. So answers on the top half of the circle. With sine, we limit, well, with the inverse sine, our range is going to be limited to negative pi over 2 to pi over 2 in order to be 1-to-1. And we're going to get the right half of the circle. So answers on the right half of the circle. And we've done that in a couple of examples. Also, just as a note, you can do these other trig functions. Tangent inverse works just the same as sine inverse. It's limited to negative pi over 2 to pi over 2. Okay. So we found some calculator answers. We found some exact answers using the unit circle. And now what we're going to do is we're going to use those inverse functions to solve trig equations. All right. Now, whenever we do this, we have to, in the back of our mind, have that understanding about where the range of those inverse trig functions are. Okay. And we'll talk about that as we go through. All right. So let's start with some basics. If I said, find an angle between 0 and pi such that cosine of that angle is equal to 0.76. Then if we said find an angle between 0 and pi such that cosine is 1.76. Well, we could use inverse cosine to solve this. We could, if we wanted to, say this is equivalent to saying that the angle is equal to the inverse cosine, or some would say arc cosine of 0.76. So arc cosine or inverse cosine of 0.76. And I would just go on my calculator. Inverse cosine 0.76 is 0.707, blah, blah, blah. So approximately 0.71 is our angle in radians. So about 0.71 radians, which is good. We wanted an angle between 0 and pi, which satisfied that. 0.71 is between 0 and pi. Remember, pi is about 3.14. So 0.71 is between 0 and 3.14. So we're done. That's the whole thing. Now, on the other hand, if you ended up with an equation like this, and you tried to solve it in the exact same way, well, if you typed in inverse cosine of a 1.76, we're going to get a no solution answer. Okay. The domain I'm just going to write this, no solution. The domain of the inverse cosine is between -1 and 1. So if I get something that's above 1 or below -1, it's not going to work. Okay. And that's also evident at this step too. Some people stop right at this step. They say, wait a second, I know cosine has a range between -1 and 1. The most cosine can get, the least cosine can get is from 1 to -1, right? Because it's an x value on the unit circle. So unit circle cannot have an x value of 1.76. So that's no solution or does not exist. I don't know what you type in, depending on what Moodle asks you to type in. It's probably going to be no solution or D&E. Okay. So we can solve basic trig equations by using those inverse cosines, inverse sines, whatever. Okay. Inverse tangents, all of that. Let's do these two as well. Now, these two say, I want to find an angle between -pi/2 and +pi/2 such that sine of the angle is a -0.82 and then tangent of some angle. These are different angles, even though I use the same theta in each equation. So tangent of the angle is -6.30. Again, notice that we're looking for angles between -pi/2 and +pi/2. This one. Because those are the outputs that we're looking for. I want you to use your calculator. Just take a moment and try to find those angles using inverse trig functions. And make sure you're in radians, just like always. All right, so in the first one, since we're saying sine of the angle is negative 0.82, then the angle has to be the arc sine of negative 0.82 or inverse sine of negative 0.82. You can use it whatever notation you like, whether you like the arc sine language or inverse sine notation, doesn't matter. But when I did that, I ended up with about negative 0.96 radians. With the tangent one, we take arc tangent of negative 6.30. By the way, that's going to give us a perfectly fine answer. Remember, the domain of arctan goes from negative infinity to positive infinity. That's while the domain of arc sine is from negative 1 to positive 1. The domain of inverse cosine is negative 1 to positive 1. Tangent goes from negative infinity to positive infinity domain. So I end up with a negative 1.41 when I do that. Okay, again, that's just plugging things in, remembering arc sine, remembering different notations that I'm writing on the board. So those are pretty straightforward. Essentially, we've isolated the sine of theta or the tangent of theta or the cosine of theta, and then we hit both sides with inverse functions. Now, if we have one of our other trig functions, something like secant. Let's say we have secant of theta is equal to negative 2.42. And we want to find the theta between 0 and pi. Where secant of that value is negative 2.42. Or, like in this next one, we have cotangent, or excuse me, 5 times cotangent of theta plus 9 is equal to 0. So this is what I mentioned last class period. We didn't do any examples yet, so these are going to be our first examples. I mentioned that these inverse secant, inverse cosecant, inverse cotangent also exist, but we can also just through algebraic manipulation use inverse sine, inverse cosine, inverse tangent when we want to, when we run into these, okay? So we'll do the algebraic manipulation because inverse sine, inverse cosine, inverse tangent are all on my calculator, all right? If I wanted to do inverse secant, well, that's not going to be on my calculator, so it's just easier to algebraically manipulate. Okay, so that's what we're going to do. So let's do secant. What I do is I think of this as 1 over cosine . So secant is 1 over cosine. So 1 over cosine is negative 2.42. And then however you want to think about algebraically manipulating, I think let's just take the reciprocal of both sides. If I take the reciprocal, I get cosine theta is equal to 1 over negative 2.42. You can also do that by multiplying both sides by cosine and then dividing both sides by the negative 2.42. So you can do that through multiplying and dividing both sides as well. Or just thinking of reciprocal, that's fine too. And so then theta becomes the inverse cosine or the arc cosine of 1 over negative 2.42. When I did that, when I round the 2 decimal places, I actually get 2.00. It's 1.996. So that 99 would round up to a 1. We get 2.00, rounding to 2 decimal places. Again, if you want to write cosine with the -1 sign, inverse, that's fine. Everybody all right with that? So there we are. That's it. So if we're given secant, we can do it that way. Here, we would want to isolate the cotangent before we do anything. So we would get 5 times cotangent is equal to -9. Then divide both sides by 5. We get cotangent of theta is equal to -9 over 5. I'm going to use the reciprocal identity, that the reciprocal of cotangent is tangent. Therefore, tangent of theta has to be the reciprocal of this. The reciprocal would be -5/9. Everybody okay with that? So just using the reciprocal identity there. You could have also wrote this as cosines and sines and did some more algebraic manipulation to get down to this, but you'll eventually get to this. And therefore, my angle is going to be the arctan or the inverse tan of -5/9. I end up with an angle of about -0.51. That makes sense? So that's the algebraic manipulation when we have secants and cotangents and cosecants. I didn't do one with cosecant, but we did the same thing with that too. We'd isolate and then solve. Okay. One of the things that we have to be aware of always in the back of our head is these domain restrictions. Okay. Usually, sine inverse of sine is x, but that's not always going to be the case if x doesn't fall within that certain domain or range. That makes sense. If my angle is not from negative pi over 2 to positive pi over 2, then I might get something slightly different. And the same goes with every other trig function too. If we're talking about cosine, then that angle should always fall between 0 and pi. With tangent, it's going to always fall between negative pi over 2 and pi over 2, same with sine. So if our original input doesn't fall within that range, then doing a sine inverse of sine of x is going to come out not equal to x. If it does fall in that range, it's going to come out as x. That makes sense? Now, the nice thing is if you hit it on the other way, so just be careful about that. Just be careful about that. And I will just kind of talk through these, show the calculator on these, that kind of stuff. But if you take sine inverse of sine of negative pi over 6, negative pi over 6 is between negative pi over 2 and positive pi over 2. So that's going to come back out as negative pi over 6. Does that make sense? So that first one, when I input negative pi over 6, is going to come out as negative pi over 6. However, on the second one, where we have arc sine of sine of 11 pi over 6, 11 pi over 6 is not between negative pi over 2 and positive pi over 2. Okay, so that one is not going to come back as 11 pi over 6. I will just hit that with my calculator and show you what's going on. Well, let's start with the pi over 6 one. Okay, negative pi over 6, excuse me. So if we did inverse sine of pi over 6, notice I'm all in radians there. Calculator mode. I get that, which is, oh, I have to put a positive, excuse me. I want to put a negative in there. Negative pi over 6. I get a negative pi over 6. That's the decimal version of negative pi over 6. Okay, so I get that back out. But if I did 11 pi over 6, I get back out negative pi over 6. Does that make sense? By the way, if you realize where the 11 pi over 6 is, that's actually a coterminal angle with negative pi over 6. It's negative pi over 6 just plus 2 pi. Does that make sense? So that's why we're getting back negative pi over 6 when we input an 11 pi over 6. Because those are coterminal. Now, you're not always going to end up with coterminal angles Like on this next one where it says our cosine of 8 pi over 5. 8 pi over 5 is more than pi. So if I put this into my calculator, I'm going to get out a 1.2566 blah, blah, blah. That is not 8 pi over 5. That makes sense. So that's not 8 pi over 5. 8 pi over 5 would be 5 point something or other. By the way, notice these are not coterminal. The difference between those two values is not 2 pi. What's happening in this case is the following. 8 pi over 5 on the unit circle is shooting us, where is it shooting us? Oh, yeah, shooting us somewhere down here. Okay? Because we're dealing with cosine, inverse cosine gives us answers on the top half of the unit circle. So what it's doing is it's giving me the answer for that angle up there. Okay, this angle here, which has the same cosine as that. Same x value on the unit circle. So 8 pi over 5 is this angle right here. Cosine only deals with the top half of the circle. So it's giving me the angle on the top half of the circle with the correct cosine. So it's not giving me the coterminal angle. It's giving me reflected across the x-axis angle. Those are kind of your two options. You're either going to get something that's coterminal, or it's going to be reflected across the x-axis, or reflected across the y-axis, or in the case of tangent, reflected through the origin. In the case of cosine, it'll be reflected sometimes across the x-axis. In the case of sine, since sine is the right-hand side of the triangle, it could give you reflected across the y-axis. In the case of tangent, since tangent is the right half, it goes through, reflected through the origin. And that's what's going to happen on this next one. If you take inverse tangent on your calculator of tangent of 5 pi over 6, once again, you do not get 5 pi over 6 back. You get negative pi over 6. Okay. And that's reflected through the origin. You think about where 5 pi over 6 and negative pi over 6 are. Because of the way tangent works, that's what happens. Is everybody okay with that? Okay. I won't belabor that point. There you go. By the way, if you do this in reverse, as long as we have something that's legitimate to plug in, we're going to get no problems. Okay. If we do the arc sign first and then hit it with sine, we should get back a negative 0.56. Try that on your calculator. As long as we're putting something that's legitimate in the domain, we're good to go. Same thing with cosine. If I have cosine inverse of negative 0.87, then hit that with cosine, I get negative 0.87. If I do that with tangent, tangent of tangent inverse 2.36, get back 2.36. So if you hit it in this way, where the interior function is the inverse trig function and the exterior function is the trig function, as long as I have legitimate values in the domain, it does give me the identity. Right? The reverse was not true unless we had inputs that were between the right values. For cosine, between 0 and pi, and for sine and tangent, between negative pi over 2 and positive pi over 2. Okay. Now, lastly, if we want to graph inverse cosine, remember inverse function changes the roles of x and y. So we're going to take our cosine graph and change the roles of x and y. Because it has this wave, we have to limit the domain and range. That meant that if we want to graph inverse cosine, it's going to be small. We're going to limit the domain and range so that we have a one-to-one function. And it's just going to be this piece. Okay. This piece going from x values of -1 to +1, and then the y values go from 0 to pi. So it is not infinite, it's limited in that. The same thing would be true for cosine, or as cosine would be true for sine inverse and tangent inverse. We're going to have to limit sine inverse. The x values are limited between -1 and 1, and the y values are limited between negative pi over 2 and positive pi over 2. Tangent inverse works a little bit different because the x values could be infinite. We can plug in anything from negative infinity to positive infinity, but the y values are going from negative pi over 2 to positive pi over 2. So they look like this. By the way, I just want to point out now, well, let me go to the next one. We're going to point out, in our last section, we saw that the sine function and the tangent function were both odd functions. Because of that, inverse sine and inverse tangent are also both odd functions. And you can see that in the way the graphs work. Notice that the graphs are symmetric with respect to the origin. So any ordered pair on one side of the origin reflected through the origin will give you another ordered pair on the graph. And that means if I plug in a negative x into the sine inverse function, that's the same thing as the negative of the sine inverse of positive x. And that's similar with tangent as well. On the other hand, because of the way I had to do the domain and range of the cosine function, notice that the inverse cosine function, I cannot reflect that across the y-axis. Notice that? If I reflect across the y-axis, I should say I don't get the function back. Like -1 pi reflected across the y-axis would be +1 pi. That's not on my function. So if I reflect across the x-axis or the y-axis, I don't get my function back with the inverse cosine. And that means while we saw cosine was even, inverse cosine is neither even nor odd. And that has to do with the restrictions on the domain and the restrictions on the range of the inverse cosine function. Does that make sense? Yeah. So inverse cosine is not even. That's something a lot of people get wrong. They think, oh, sine and tangent are both odd, so the inverse sine and the inverse tangent are both odd. So you expect that cosine being even gives an inverse cosine that's even, but that is not the case. Because of the restrictions, inverse cosine is neither even nor odd. Okay, there we go. Any questions about these inverse trig functions? Again, the big thing is understanding where the domains and ranges are. Hopefully, I've put quite a lot of emphasis on that. So that's it for chapter 6. Okay. That's it for chapter 6. We're going to use a lot of the things we learned in chapter 6 in these next couple of chapters, in chapter 7 and chapter 8 as well. But the actual sections we're covering in chapter 6 are done. Okay. Now we go into chapter 7. And chapter 7 is probably the most unique chapter of the course. Right? Chapter 7 is on trig identities. That's why we have this big sheet that I handed out of trig identities. Okay. These are all things from chapter 7. Some of them we've already seen before, like the reciprocal identities and quotient identities. The Pythagorean identities we saw, some even and odd stuff we've seen. But the essence of trig identities is that we want to simplify, we want to rewrite, we want to have trig functions and be able to rewrite into other trig functions. So we're going to start with some basic relations between the trig functions. And we're going to build on top of that other relations that we could have. Okay. This way we can use those things to simplify, to rewrite, to solve. Now, the difficulty of chapter 7 is that there's lots of identities. And almost all of them are related in some way. Many, many are related. And what this causes us to have is a lot of different routes or routes. Okay. I want to get from point A to point B, but there's tons and tons of routes that I can take. Now, some of those will lead me to where I want to go. So there's some routes that go to where I want, but there's also going to be times in which we start going down a route and it doesn't lead us to a useful place. Okay. The analogy that I use is like being in a forest, right? I want to go from point A, let's say on one side of the forest, to point B on the other side of the forest. And let's imagine that this forest doesn't have like a nice paved path through the middle of it, like a lot of parks do. This is an actual forest where, a lot of people aren't in all the time. Well, there's going to be lots and lots and lots of different paths through this forest. And if you started at point A and I started at point A, you might take one path and I might take another path. And we might both end up at the correct place on the other side of the forest. Okay. You might take a left at this tree and I might take a right at that tree. And we'd all end up at the same place and we'd be all right. On the other hand, as you move through this forest, you might start moving through this forest and get lost. And all of a sudden you come back out at point A where you started. And you think, oh crap, something went wrong. Okay. But there's not a well-defined path. That's the whole point. Okay. A lot of other mathematics, there's a really well-defined path going from point A to point B. When we're trying to, solve right triangles, it was pretty straightforward. I could use this tool or this tool or this tool, use them, find all the angles, find all the side lengths. Here, it's not quite that straight. So a lot of people struggle with it because of that. Okay. You guys know Robert Frost's poem, Road Not Taken? Ever hear of that? Okay. This is one I like to talk about, not in the context of trig identities. Right? There's going to be paths. There's going to be times where you emerge, and there's going to be a couple of different ways presented to you. All right. And you got to choose one. I won't read the whole poem. Okay. But there you go. Two roads diverged in Yellowwood. That kind of thing. So, like I said, this is my forest analogy. The other thing I'll say about this is that the worst thing that happens is people start going down a path and they get frustrated. And the worst thing a little kid can do in the forest is like sit down and start crying and not moving, right? If you get into a forest, just sit down and stop moving. That's a bad thing. That's a bad way to get from point A to point B anyways. So keep moving. Even if you do a couple loops back on yourself, come back to the wrong spot or get out at the wrong spot, right? Don't sit down and start crying when you're doing these problems. Make sense? All right, good. Okay. So let's look at some base relationships. We've already seen some of these. These are our reciprocal relationships. We start out with knowing what cosine and sine are. Tangent is sine over cosine. That's the quotient identity, by the way. What's that called? Cotangent is cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine. Okay. That means tangent and cotangent are reciprocals of each other. Secant and cosine are reciprocals of each other. Cosine, cosecant, and sine are reciprocals of each other. Okay. Okay, so tangent and cotangent, those are called the quotient identities. What we just said, these are the reciprocal identities. Okay. Again, all of these are provided on that trig identity sheet. If you've lost that, I have more of those. And so, yeah, you just ask me. Also, they're up online through Moodle too. Okay. The other identity that we've seen before is the Pythagorean identity. We showed that with the cosine squared plus sine squared equals 1. That comes from the equation of a circle. And then the other two come from dividing that Pythagorean identity by either cosine squared or sine squared. Actually, you can get those in a different way too. You can get those through a different, using a different right triangle on the unit circle. Does that make sense? I'll show you real quick on that, just because it's kind of interesting. Hopefully I can pull it up. Hopefully I got it though. Let's see if I can find it. Don't have it on this one. This account. Hold on for just a second. So the right triangle that we usually focus on with the Pythagorean identity is this one that goes through my cosine sine. This value is cosine, this value is sine. So, and because the radius is 1, the hypotenuse is 1, right? So that's where we get the standard Pythagorean identity. It turns out that there's another line on here that gives you the other trig functions. It's going to be anyway. Oh shoot, I should. That's what I did. I had it right and forgot the negative sign. There you go. It's this one. Okay. We see that blue line there? That blue line actually gives you all of the other trig measurements. Okay. So if you wonder what tangent is on the unit circle, tangent is actually the measurement from this point on the unit circle all the way out to whatever this length here, from there to there. And cotangent is from here to here. That makes sense. And then secant goes, it's the measurement from my origin all the way out. Okay. So if you, see if I can get a good color, we'll go green. If I look at this triangle, the one that goes there, there, and there, this is 1. That's because that's radius of the circle. This side is tangent, and this bottom side is secant. And the way I drew this line, those are perpendicular slopes, so that's a right triangle there. Okay. You guys ever see that? The tangent secant on the unit circle? That's how it's labeled. So 1 tangent secant, that gives us that right triangle. Again, our standard right triangle that we use is the one where this is cosine. I'm trying to draw with my mouse, so that's not very good, but this one's sine. And this is a 1, because that's the radius of the unit circle, right? So that gives us sine squared plus cosine squared equals 1. The other right triangle gives us the tangent secant 1. And then there's a third right triangle. Oops. Oh. I didn't draw this very straight, but that's okay. Terrible. Let me clear that. I'm going to move up and to the right today. There we go. That's the third right triangle in that picture. And this is cotangent. This is 1 because that's the radius of the circle. And this measurement here is cosecant. Is that right? By the way, that's why the cotangent and cosecant are called co. That's why the prefix is co. All right? Because if you think about this being your angle theta, all right? This is some other angle. That other angle will be, if you're talking about degrees, 90 minus theta. All right. So that's where we get the oh. Right. That work? All right. That's a long explanation. I should have had that drawn up. I thought I had it. I did have it, just not in the right place. So good enough. But that's another way to get those other two Pythagorean identities, is to look at the unit circle with those other two triangles. Okay. Even oddness of cosine, sine, and tangent, we saw that In section 6.1, cosine is even. So if I put in a negative x and put in positive x, I get the same thing. Sine and tangent are odd. So if I put in a negative x, I get the negative of what I get out when I put in a positive x. Again, these are the even odd identities on those. Now, the other algebraic tools that we're going to use, we have reciprocal identities, quotient identities, Pythagorean identities, even odd identities. The other tools that we're going to use, at least in this section, are just standard algebraic tools. I want to be able to multiply both sides by 1, or multiply both sides of a fraction by 1. Multiply the numerator and denominator by the same number. I want to understand how to get common denominators. I want to factor and be able to understand factoring and canceling out factors and all that stuff. So all of the other algebraic tools that we know how to do. So if I put in those identities along with a bunch of other algebraic tools, I can rewrite a lot of expressions. The two types of questions that will be asked most often are to verify whether an equation is true or not, and to simplify and rewrite it. Whenever we do this, either verify an equation is true, we'll assume denominators are not 0. Same thing when I simplify and rewrite, we'll assume denominators are not 0. But those are the two big questions. We'll use all of those tools. We'll have this great big bag of tools, and we'll answer one of those two types of questions. Okay. Again, go back to our forest analogy. Because we have so many tools, we're going to have a lot of options. And this is where some people get frustrated with this chapter, because they'll say, well, where do I start? There's no clear sign that tells me to use this tool or this tool. And again, you just have to learn to navigate the woods, right? Navigate through the forest. And once you're in the forest long enough, you'll start seeing patterns and signs and noticing those things, just like an old trapper would. Does that make sense? You guys know, like Davy Crocker and Daniel Boone and all those trappers that went through the Appalachian. All right. So that's what I'm talking about. So let's try to decide whether the following statement is true or false. Cotangent of theta divided by cosecant of theta is equal to sine of theta. All right. So probably what I would do, again, you can do a lot of different stuff, but probably what I would do is I would rewrite cotangent using sines and cosines. So cotangent is the fraction cosine of theta over sine of theta. Cosecant is 1 over sine of theta. Now, as long as we know how to divide fractions right now, we're going to be done. When you divide fractions, essentially these denominators being the same are going to cancel each other out, and we'll get cosine over 1. Does that make sense? The reason why those denominators cancel out is because, I'll write it this time, I usually don't write this step, but is because dividing by a fraction is the same thing as multiplying by the reciprocal of that fraction. So if I multiply by the reciprocal, I'm multiplying by sine of theta over 1. Those sine of thetas are going to cancel each other out. And I'm just going to get cosine over 1. So whenever I divide fractions, those fractions have the same denominators. Those denominators will just cancel each other out. In this case, we're left with a statement which says cosine of theta is equal to sine of theta. And for arbitrary values of theta. That's obviously false. Cosine and sine are not the same function. And therefore, we can say that since this is false, my original statement would have also had to have been false. Any questions about that? Now, that's probably the easiest path to go through this. There are other ways you could have gone through this. You could have tried to multiply both sides by cosecant. Does that make sense? You could have done that. So let me just go through that other path, or one other path. If you said, well, let's start this expression and multiply both sides by cosecant. If I multiply the left by cosecant and multiply the right by cosecant, cosecant and sine are reciprocals of one another. So when I multiply those, I get a 1. Does that make sense? Cotangent, once again, is cosine over sine. And then if you wanted to, you can multiply both sides by sine. Or you could say that because a fraction is equal to 1, then the numerator has to be equal to the denominator. And that's another path I could have taken and got the same answer. And notice that the statement therefore has to be false. So it's a combination on both of these. It's combinations of being able to rewrite cosecant, cotangent and understanding how algebraic manipulation works. And if you went this path and somebody else went this path, you both got false, that's perfectly fine. Okay, ended up at the same spot on the other side of the book with slightly different paths. Now let's do the other type of problem. The other type of problem is to rewrite and simplify. Or sometimes it just might say simplify as much as possible. Here we have negative tangent of negative x times cotangent of negative x. Again, multiple paths of doing this. What I would probably do is I'd probably get rid of the negatives on the inside as much as I can right now. I know tangent is odd. I also know cotangent is odd because it's the reciprocal of tangent. So I'm going to have negative. I can pull out a negative, and I can pull out a negative there. So I get essentially 3 negatives in front. Which is going to give me a negative tangent times cotangent. So I had one negative already out in front, pull this one out in front, pull this one out in front. So I got 3 negatives out front, negative times negative gives me a negative. X. What's tangent times cotangent and why?
Tangent sine over cosine and cotangent cosine over sine.
Okay, so sine over cosine times cosine over sine.
So it's just 1.
And yeah, so we get a lot of these canceling out. So we get -1 as my final answer. That's the simplified version of the negative of tangent of negative x times cotangent of negative x. Now, this is using the quotient identities for tangent and cotangent. Right? If someone else said, I want to take negative tangent of x times cotangent of x, and I want to use the reciprocal identity on cotangent, they would have also canceled out, although they would have canceled out tangents and ended up with a -1. So again, these are the slightly different paths you can use. If you want to use reciprocal identities, that's fine. If you want to use quotient identities, that's fine too. In this case, both of those lead to the same outcome. Let's get slightly more involved. We have tangent theta divided by secant theta times sine of negative theta is equal to cosine squared -1. cosine squared of theta minus 1. We have lots of different things we can throw at this one. Okay. Now, again, it takes some time to like get used to how these things are going to go and what side to start with and what side to end with and all that kind of good stuff. But in this case, what I would do is I'll start by rewriting my tangent and secant into sines and cosines, so we can see that. So tangent is sine of theta over cosine of theta, divided by secant, which is 1 over cosine of theta. Now, because sine is odd, I'm going to pull the -1 out right now. Okay, so that's -1 times sine of theta. There. So if this is true, then this is also true. That's what we're saying there. This first equation's true, then this one's true. These are equivalent equations. I can see now that denominators of cosines are going to cancel each other out. Again, that's multiplying by the reciprocal. So cosine here and cosine there are going to cancel each other out. It is twice. When I, flip and multiply. So I'm going to end up with sine times -1 times sine. Sine of theta times -1 times another sine of theta equals cosine squared theta minus 1. By the way, this whole thing on the left-hand side is negative sine squared of theta. Sine times sine is sine squared. And now again, we have options. What do we want to do? I think the easiest way to see this is to probably add sine squared to both sides. Sine squared of theta. And then I'll probably add 1 to both sides as well. When I do that, I get 1 is equal to cosine squared theta plus sine squared theta. That's true, right? That is that's our Pythagorean identity. Our first one. So that's like saying 1 is equal to 1, that's true. So since this is true, and this was equivalent, 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 that means my original equation was true, as long as I don't have any zeros in denominators anyway. Okay. That makes sense? So this being true means that this is true as long as there's no zeros in denominators. When there's zeros in denominators, everything goes wonky. So this is another identity that we can come up with. Now, is this one worth memorizing? Probably not. Okay. There's only really a handful that are even worth memorizing. Most are not worth memorizing. Definitely not something like that, because that can be derived from the other similar ones. Okay. Oh, by the way, on that last example, example 3, I showed you one path. There's lots of other paths too. And some of them are more complicated. Some of them might be less complicated, but I tried to use the most straightforward path that I could think of at the time. Let's do another. This says rewrite and simplify the following. 1 plus sine of x times the quantity 1 plus sine of negative x. All right, what I would do is I'd probably rewrite this using even odd identity. That would be 1 minus the sine of x in the right hand expression. Right, the one in the right hand side parentheses. So since sine is odd, I can pull out the negative on the outside. Now when I multiply, I'm going to get 1 times 1 minus sine of x times 1. Sine of x times 1, that's plus sine of x. And then sine of x times negative sine of x gives me minus sine squared of x. Sine x times sine x is sine squared. Notice that the two middle terms cancel each other out. So I get 1 minus sine squared. There. If I want to rewrite this, one way I could rewrite this is I could rewrite this as cosine squared of x. If I want to make it a monomial term, single term. Does everybody understand where I'm getting that exchange from? I'm getting that exchange from my Pythagorean identity, where I just subtract sine squared from both sides. So 1 minus sine squared is the same thing as cosine squared. So if I want to simplify the terminology as I can, this expression is just cosine squared of x. I can't really break it down further than this. That makes sense? So these Pythagorean identities also can do the exchanges, and for cosine squares, can do an exchange for 1 minus sine squared. If you get into tangent squareds and secant squareds, I can do those exchanges, and cotangent squareds and cosecant squareds can do those exchanges as well. In fact, in our previous example, I moved around the cosine squared and sine squared to the same side. Okay, some people would have done the exchange and then subtracted. And that's another option that we have. I want you to try to navigate this. This is true, false. And it's asking, is this statement true? And how could we show it if it is? This is a very nice one because we could do this in a lot of different ways. In fact, I'll show you once you do this. I want you to try it on your own first. But I'll show a couple of different ways of how it could be done. It's not exactly what teaching. Because then it's -1. You couldn't cancel this 1 -1. You get tangent squared over this. Doesn't help you that much. So I'm not saying that this is the wrong answer. My feature might be false, but I'm saying you can't cancel this way. That's algebraic violation. Does that make sense? What I have to do. There's a number of ways you can do this. Take everything in the cosines and sines. Or you can do this like you're doing. Place this, you can square. Plus being 1 and -1 is like left tangent squared on top. Bottom of the secant squared. We should multiply both sides by secant squared. Oh, there. Yeah, but it's negative one. You can still go. So you can do that, and give you one. Okay. One, so they don't cancel out the zero, cancel out the one. One, but minus one over inches. Right. Oh. I don't know about all those, but. All right. So let's go through this one. And we'll do this in different paths. This one is a very interesting question because there are a lot of different ways we can approach this. Okay. For one, I saw some people start dividing. Now, if I'm going to divide, that's perfectly fine. I just have to divide correctly. Since I have a single term in the bottom of this fraction, but for subtracting two terms on top, when I divide, I have to divide the first part over secant squared, and then also divide the second part over secant squared. That would be fine to do. We'd get 1 minus the reciprocal of secant squared. I'll rewrite that. Secant squared is 1 over cosine squared. Notice that if you do 1 over cosine squared, that's just cosine squared. So the reciprocal of secant is cosine. So we get 1 minus cosine squared theta equals sine squared theta. Now that's going to be true by the Pythagorean identity. You can add cosine squared to both sides if you wanted to. And so that's true by the Pythagorean identity right there. So if you divided each piece by secant squared to start with, you'd be good to go. That'd be fine. Another technique that I saw was looking at, since this was dealing with secant squared minus 1, if I look at my Pythagorean identities with tangent and secant, we have tangent squared plus 1 is equal to secant squared of the same angle. So what I could do is notice that secant squared minus 1 can be replaced with a tangent squared. Therefore, in this numerator, I could write tangent squared of theta. The denominator I'm going to keep as secant squared of theta for right now. Equals sine squared theta. Okay. What's tangent? Tangent sine over cosine. So tangent squared is sine squared over cosine squared of theta, obviously. Secant squared is 1 over cosine squared. And if you divide, cosine squareds and the denominators will cancel each other out. And you'll just be left with sine squared is equal to sine squared. That's obviously true too. So that's another option, if you like. Another option, what we could have done. Another thing we could have done is kind of a combination of what we did in just the previous one with multiplying both sides by secant squared. So if I multiply both sides by secant squared, secant squared is 1 over cosine squared of theta. Secant squared minus 1. We just said that's tangent of theta earlier. So that's tangent of theta on the left. Tangent squared of theta, excuse me, on the left. And this is sine squared divided by cosine squared, which is also tangent squared of theta on the right. Again, that's another true statement. That work? Let me just give you one more to deal with. Okay. What if I said instead of, this is more closely related to the very first one we did, let's multiply both the top and bottom of this left-hand fraction by cosine squared of theta. So that's just multiplying algebraically by 1, right? Cosine squared over cosine squared. Now, here's the nice thing. If I multiply cosine squared by secant squared, that's going to cancel out and give me a 1. You guys understand why? Secant is the reciprocal of cosine. So cosine squared times secant squared is 1. So cosine squared times secant squared gives me 1. Cosine squared times minus 1 gives me minus cosine squared. And that's going to be all over 1, which I could leave off if I wanted to. And now I get something very much equivalent to the last steps in the first way I solved this. That's my Pythagorean identity, so that's true. Okay. Now these aren't, I've given you 4 options that have all shown us that we can get true in different ways. These are not the only 4 options though. There's lots of other ways we could have gone about this. We could have broke down those secants and we could have immediately written those in terms of cosines. We could have, since this is 1 over cosine squared, I could have wrote 1 as cosine squared over cosine squared and went through it that way. It would look very similar to what we were doing over there. But you could do that if you'd like. Let me go ahead and just do that. 1 over cosine squared, just so you can see what I'm saying. Since this has denominator cosine squared, I'll write 1 as cosine squared over cosine squared. And then I'd combine those fractions in the numerator. And then I'd see that the cosine squared would cancel out. I'd end up with 1 minus cosine squared. All of this right-hand side hasn't changed. And then add cosine squared true, right? So you could have broken it down that way as well. And you see the issue, right? The issue is, if I told you, well, this is the only path you could take, it would not be the only path you could take. There's lots of different ways we can go around, getting from point A to point B on this problem. So, whichever way you like, and whichever way probably is most straightforward to you. Sometimes I might like something that is done one way, and another person might like something that's done another way. So somebody might say, well, instead of writing this as sine over cosine and 1 over cosine, rather, let's multiply both sides by secant. I know secant's 1 over cosine, and then we could have done something like that. So multiply both sides by secant squared. So you can see tangent squared is equal to tangent squared.
That's exactly what I did actually.
Yeah, so exactly. So there's a lot of different ways of doing these and doing combinations of those. That's kind of like a combination of this one and the one we did right here, right? Multiplying by secant squared on both sides. So yeah, lots and lots of different combinations of things we could do. Lots of paths we can take. This one, there's probably a few less paths you can take. So go ahead and try this one on your own as well. This one, there might not be so many trees in this forest. Be careful when you square sine plus cosine. Remember to do sine plus cosine times another copy of sine plus cosine. All right, this one's a little bit, like I said, more probably straightforward of how most of us would approach it. Because this one has sines and cosines. When we see secants and tangents, a lot of those ones, we tend to end up with more paths because you can rewrite secant as 1 over cosine. You can rewrite tangent as sine over cosine. And so there's a couple of different things you can apply. When we have just sines and cosines, we tend to stick with sines and cosines, tend to. So there's usually less options to go with. What I would do is I'd start algebraically manipulating. This thing squared is it times itself. This is like polynomial multiplication, binomial times binomial. We get sine squared of x. Sine times cosine, both of x. Then this gives me cosine times sine. I'm going to write that as sine times cosine so that the order matches my other one. And then we get cosine times cosine, which is cosine squared. Now you can do the next step in 2 parts. I'm going to kind of do 2 identities in one. I'm going to notice that on this left-hand side, I have a sine squared plus cosine squared. The Pythagorean identity can be applied to sine squared of x plus cosine squared of x. I know that is 1. So that's 1. And the other thing is I'm going to combine those 2. That's 2 sine x cosine x. So my left-hand side simplifies like that. My right-hand side is 1 minus 2 times sine x times cosine x. Is that the same thing? No, that's different. One of them has a minus, one of them has a plus. And if I subtract 1 from both sides, I get a positive 2 sine x cosine of x versus a negative 2 times sine x cosine of x. That's obviously false. Unless you always get 0, which you don't, obviously, for every value of x. So this is false in general. And so that means that one's false. However, notice if I put a plus sign, it would have been true. Right? If I'd have changed that one little bit from a minus to a plus, it would have been true. But as it stands now, that's false. Any questions about that? No, pretty. Again, if you want to go more steps, you can go more steps, but I don't think it's necessary right here. A lot of times, that's the other thing. A lot of times, what I would have probably done is I would have probably stopped at this stage. You don't really need this stage if you can see that this is clearly not the same on both sides. So once you realize that both sides are not equal for all values of x, then you can just say it's false. By the way, there will be some values of x where that will be, right? For instance, like if x is pi or pi over 2, then those 2 sides will be equal because I get zeros there. But for other values, most values, it's false. And that's a good note that when we're saying true or false, we're saying true or false for all x values or for all values of theta. Okay. Try this one. Is this one true or false? Couple of different methods you could apply if you wanted to. I'd probably use even odd stuff to begin with to get rid of the negative angles inside my argument. All right, let me go through, I'll do this in a couple different ways. The two ways that I would do this. So the first one, factor out the negative from the negative sign, put it on the outside because sine is an odd function. By the way, what would have happened there? Maybe I should have said this. We have sine squared. What will happen if I do that?
Would that just be sine because it's
Yeah, there's two of them there. So just be careful about that. So when you take this negative sign out, you actually have to take it out twice because it's sine of negative theta times another sine of negative theta there. So you take out the negative and then the negative, so you're going to get a positive sine squared. You understand that? So positive sine squared. Here, there we go. So be careful taking things out of negative sign squared. In fact, what I would probably do is I'd put a -1 squared on the outside there. Now cosine is even, so this will absorb the negative, right? Cosine of negative theta is the same thing as cosine of positive theta. So the square is not going to affect that at all. On the bottom, I will have a negative sine theta. There's just one copy of sine on the bottom there. And this is a minus cosine theta. Remember that? What I would do on the left-hand side is I would multiply both sides by this denominator. I'm not going to write that out because that'd be a lot of writing, but I'm going to multiply both sides by the denominator. And on the left-hand side, that's just going to give me sine squared minus cosine squared is equal to negative sine theta minus cosine theta multiplied by cosine theta minus sine theta. That's the big thing. A lot of times when we have odd functions, people try to plot a negative. They forget that's an odd function squared. So when you pull out a negative, you got to square the negative as well. All right. So multiply both sides by denominator. What I'm going to get is negative sine times cosine. Then negative sine times negative sine, that's going to be a plus sine squared. Negative cosine times negative cosine, that's negative cosine squared. And then negative cosine times negative sine gives me a plus sine times cosine. Notice what's going to happen. This term and this term are going to cancel each other out. And I have the exact same expression on both sides. Sine squared minus cosine squared equaling sine squared minus cosine squared. Okay. And so that's true. I could put it in one block. Let's see what I got there. By the way, notice that if I'd have screwed up that pulling out the negative, I would have ended up with a false statement. So be careful about pulling out those negatives, especially in under squares. Any questions about that process, that technique? The other technique that you could have done is very, very similar. At this point, where I had sine squared minus cosine squared on the top, and then this would have been a negative sine of theta minus cosine of theta on the bottom. I could have factored the top knowing the difference of squares formula. You guys know what I'm saying by difference of squares formula? So if I had a squared minus b squared, that's the same thing as a plus b times a minus b. That factoring, that factorization. I could have applied that here where A is sine and B is cosine. Okay, and if I did that, I would have had sine plus cosine of theta, obviously, times sine minus cosine. And then if you notice the bottom, it's -1 times sine plus cosine. On the right-hand side, we still have cosine. This theta looks bad. Theta minus sine. Okay. Okay. And what would have happened is that this term and this term would have canceled each other out. I had sine minus cosine divided by -1. That's a negative sine plus a cosine is equal to cosine minus sine. Same thing. So I could have done it by factoring and using that difference of squares factorization as well. Okay. Is that all right? So lots of options that we could employ. Now I'm going to skip one of the examples. I'm going to skip example 8 and go right to example 9. This one, instead of a true or false, is one of those rewrite and simplify. Okay. I want you to rewrite and simplify. Try to make it as simple as I can make it. Might turn out very simple. Might turn out, well, simpler than this, but not quite super simple. Maybe it's 2 ways. All right, since we have little time, let's ask this. Any preference on how you start this? Go for it.
You can turn the one on top into sine squared, right?
Exactly, yeah. Pythagorean identity says cosine squared plus sine squared is equal to 1. So when I subtract cosine squared from both sides, I get that identity. I obviously didn't write the argument. So I can put 1 minus cosine squared is sine squared. And then I could, if I wanted to, put tangent as sine over cosine. So tangent squared is sine squared over cosine squared. And then dividing by a fraction is like multiplying by the reciprocal of that fraction. So I could take sine squared of x and multiply times the reciprocal of the fraction. Plus. Sine can cancel out. So sine squares will cancel out. And I'll just be left with cosine squared plus sine squared. Which we all know, Pythagorean identity simplifies to 1. So that expression is just 1. Okay. Given any angle that you can plug in and not be dividing by 0. So as long as you're not dividing by 0, that expression. Okay. Any other ways people would like to start? Go for it.
I turned tangent into sine over cosine immediately.
Yep, and then multiply by the reciprocal immediately. Perfect. So we can do that as well. We can go 1 minus cosine squared, turn tangent squared into sine squared over cosine squared. And then I would probably now multiply by the reciprocal. Okay. 1 minus cosine squared of x all times that way. Now, at this stage, did you rewrite this?
No.
No, so you multiplied it through.
Yeah.
Okay, so let me think about how I do that. So cosine squared of x over sine squared of x minus, this would be cosine to the 4th. Over sine squared of x plus sine squared of x over 9. Okay. Where'd you go from there? Or did you go from there?
I didn't quite do it that way.
Oh, you did a different way. I'm sorry.
Yeah.
I thought
I did the start the same, but
started the same.
I think I might have messed up somewhere, but I got it is weird.
No, that's perfectly fine. Now, here's the thing. Sometimes when you're walking through the forest, let's say I walk through the forest, I get this far, I know I'm in a bad spot. I know that this is going to be not worth my time simplifying. So I might retrace my steps and just look at stuff that happened before and start at one of the steps that I did before. And so you can go back all the way to the start, or you can just go back to this step and say, let's forget about this one. And let's rewrite this expression as sine squared. Okay. If I rewrite that expression as sine squared of x, then everything turns out nicely at this stage. And you end up with 1. Again, same thing. Okay, very, very similar. By the way, this is not the only way you could have done this. There's other ways you could have approached this. In fact, where I was at, where there's like cosine to the fourth and all that stuff, we'll see other approaches to that next time. But at this stage, for the tools that we have, probably this would be the way to approach it. Or like we did over here, change the sine squared, change 1 minus cosine squared into a sine squared right away. Does that make sense? So lots of different approaches. It's like Robert Frost said, right? 2 paths diverge in Yellowwood. Robert Frost took the path less traveled. That's not always the right one. Sometimes the path more traveled is the correct one. Sometimes the path less traveled might be the correct one. Sometimes both paths might lead to the right spot. You don't know. Okay. By the way, anybody know that there's a lot of people who interpret that poem in various ways? One way to interpret that poem is that he's very happy that he chose the path that he did. And another way to interpret that poem is that he's upset that he chose the wrong path, basically. Okay. So there's different ways to interpret that poem. But long story short, there's lots of paths through the woods, right? Lots of paths through the forest. And lots of ways to do these problems. Okay. So if you ever think about trig identities, think about Robert Frost. Good to go. All right. I'll see you all on Thursday.